My name is Alex Gurvich. I'm a PhD student in the Department of Physics and Astronomy here at Northwestern University. And today I'm going to show you how I use computer simulations to explore the universe. Now first, to do that, I have to set the stage. So this is a picture of our universe. It's a long exposure photograph taken by the Hubble Space Telescope. And in it there are thousands of objects, each one its own galaxy, each one its own size, shape, and color. As an astronomer, I want to understand why that is. What makes them different? It's hard to tell just from a picture like this for two reasons. One, because you can't see everything. And two, because you can't watch anything. So let me explain what I mean by that. You can't see everything. There are invisible components of the galaxy that determine its size, shape, and color that don't shine brightly like stars, so we can't see it in an image like this. This gas reservoir that will turn into stars, for instance. Can't watch anything. This is a static image in time. We can only see how the galaxies look today. We can't see what happened in the past. We can't see how they grew and evolved. So that's difficult. That's something that makes it a lot harder to tell, right? But that would make it seem like it's totally impossible. How can we understand where these things came from? But I have to admit there is a way to do it, because I've lied. This is not just an image of our universe, it's two. On the left is the real universe, and on the right is a picture taken from inside a three-dimensional computer simulation. In this simulation, we can take pictures from any angle, right? We can zoom in and do whatever we want. So we can see everything, because it's inside of a computer. We know where all of this gas reservoir is. We know where the dark matter is, right? We know where everything is. We can watch anything. In fact, we can watch everything, because we can play the simulation forward and backward through time. So to show you this, I have this picture here. So on the left is the invisible universe, right? In this picture, there's this reservoir of gas that will eventually turn into stars. Whereas on the right is the starlight from this galaxy. So we can start to make the connection between the two using the simulation. But even better, like I said, we can watch this forward through time, because this is not actually a picture, it's a movie. And so we can play it forward and watch how this particular galaxy assembles itself and grows and evolves, eventually becoming a galaxy that looks a lot like our own. In particular, I want to draw your attention to these dark streaks that you start to see, the shadows that the gas is casting from the starlight. This is something that we're very interested in using these simulations to help understand what we see in the real universe, because of course in the real universe all we can see are these shadows. So we can take this galaxy that we get out at the end of our simulation and flip it, right? It's a simulation, we can do that, and compare it to a galaxy like we see in the real universe. And I'd posit that these two look very similar, and in fact, what I see is that they have the same sort of spiral structure, and in particular, these dark streaks, right, these so-called dust lanes. They have the same sort of branching pattern as in the real universe. And it might be somewhat surprising to hear that this is actually a result of something that's relatively simple when we put it inside the computer. And in fact, when we take our computer, all we do is kind of teach it how gravity works. We teach it how this gas flows and interacts, the so-called equations of hydrodynamics, the same math that governs how water flows here on Earth. Then we teach the computer what it means to be a star. Right? That may seem kind of strange, but we just give it an idea of, in our simulation, what we mean for something to be a star and how they form. And that's an important piece, because we know that the size, shape, and color of galaxies is closely related to how stars form in them. So on the left is a young blue disk-like galaxy, sort of like our Milky Way, with a lot of young stars that are still blue. In this sort of galaxy, there's still a very large reservoir of gas that stars can form from. On the right, we have a so-called red and dead elliptical galaxy, where its gas reservoir has been totally depleted. So there are no more stars forming in this sort of galaxy. So we want to be able to understand, why is this the case? What happened to the gas to make this so-called red and dead elliptical galaxy? Was it just all converted into stars, or could something else have happened? To answer that question, we run these sorts of simulations, and we get a picture of what star formation looks like. Let me draw that picture for you. So star formation begins in the interstellar medium. So the interstellar medium, inter between, stellar, stars, medium, stuff between stars, is the gas reservoir that I've been talking about. This gas flows sort of like an ocean. It has currents and eddies. These eddies will eventually coalesce and form into dense clouds. These clouds will become dense enough that they'll start to cool down to temperatures low enough that they can host molecules, sort of like here on Earth. So we call these clouds giant molecular clouds, GMCs. Gravity is going to take these GMCs and try and shrink them down to a point, right? They're just stuff. There's nothing to hold it back. Eventually, it becomes dense and hot enough that it sparks nuclear fusion, and you get a star that forms. Now, the star will spend the rest of its life trying to fight off the advance of gravity. It will burn its fuel, right, the gas that came from its host GMC, making heavier and heavier elements as it does it to push back the onslaught of gravity. A lot like Atlas holding up the sky, right? But eventually, this can't continue because it will burn up all of its fuel. And once a star's fuel is exhausted, it has nothing to stop it from collapsing down to the point that gravity wants to turn it into. When this happens, you have a violent explosion called a supernova. These sorts of events are some of the brightest and most powerful in the entire universe, sometimes outshining their host galaxies by even up to a factor of 10 from a single star. This explosion, as it expands through the interstellar medium, will stop new GMCs from coalescing, providing so-called stellar feedback. Right? So this is sort of a feedback loop that regulates the amount of star formation that occurs inside of a galaxy. And in this way, star formation can self-regulate and form just the right amount of stars and deplete its gas reservoir at just the right rate. So this is the picture that we take out from our simulation. Does this make sense? Right? Yes. Yes, it does, I will say, because this is a real picture from our universe of M82. It is a starburst galaxy, a nearby starburst galaxy, which means it's undergoing a period of a very intense star formation, which means that it's subsequently going to undergo a period of very intense stellar death and a period of very intense stellar feedback. And as this feedback interacts with itself, enhancing itself, becoming more and more powerful, it can actually expel material from the galaxy. So we can watch this happen in the simulation and verify in the real universe that it is. That these galactic winds are a major contributor to halting star formation in very massive galaxies. So there's one more thing that I wanted to share with you today, and that's a visualization package that I built as part of my research. So this package will allow you to, from the comfort of your own web browser, explore our data set. Here I've hosted it on the web, and I want to invite you to join me and explore the universe. Thank you.